Let's next discuss magnetic field lines. Magnetic field lines were developed by Michael Faraday in an effort to describe what the heck was going on, and they work really, really well to describe a lot of things. People didn't like them because they weren't mathematical, but that's where Maxwell came in and saved the day. He said, yes, these magnetic field lines can convert to math like so, and that's how he developed Maxwell's equations. But nevertheless, even though they aren't mathematical, they describe magnetic fields really, really well. They describe both the magnitude and direction of the magnetic field. Unlike electric field lines, which start on positive charges and end on negative charges, magnetic field lines are always complete loops, i.e. they never start nor stop. The direction of the magnetic field line is just the direction of the magnetic field at that point. In other words, the direction the north pole of a compass will point when placed at that location in the magnetic field. The stronger the magnetic field, the closer together field lines are, just like with electric fields are. In a bar magnet, it has magnetic field lines that go out of the north magnetic pole and back into the south magnetic pole. But inside the magnet, these lines go from the south pole back to the north pole. And here's a picture of that. If I put a compass right here, it'll point that away, parallel with those magnetic field lines. If I put a compass right here, it'll point that away. If I put one right here, it'll point that away. If I put one right here, it'll point that away. The compass just points in the direction of the magnetic field. If I put one here, it'll point that away. So these magnetic field lines, they're pointed out of the north, and they're pointed into the south like this, and then they go all the way around in a loop like this one right here. Big loop, goes out of the north, back into the south, but inside the magnet, the loop direction continues from south to north. Out of north, back into south, but then inside the magnet, continuing from south back to north. So let's go ahead and show this.
The field lines seem to go out of the north pole of this thing, and they curl around and go back in to the south pole. This is just pieces of staples. That's all this is. And you will see them all line up like little compi, but this will help us get a better understanding of what the field looks like. They are all lining up with the magnetic field.
Here's just a sketch of a magnetic field due to a bar magnet. Notice the lines come out of the north, they circle around, go back into the south. Inside the magnet, the field lines are very close together. Right here, close together right there means the field is strong. They're also strongest outside the magnet near the poles. As you get farther away from the magnet, these field lines get farther apart. So that's an indication that the field is getting weaker as you get farther away. That's no big surprise. Typically, they're strongest by the poles where we can get to it. It's very hard to get inside a permanent magnet there. We can get inside an electromagnet, as we'll see. Notice that the field lines cannot cross. A little bit messy there, but they can't cross simply because a compass can only point in one direction. The north pole of a compass can only point in the direction of the magnetic field. Can't point in two directions at once. So magnetic field lines do not cross because at any point, the magnetic field has one specific direction.